And we made a little something called a mistake. And let's talk about the mistake we made. I'm actually glad I made it kind of because it's a very, very common mistake. Let's have you not fall into this mistake. So here's the deal. I made the argument that I had to be bigger than I had to be bigger than equal to 1 because that made I plus 1 bigger than equal to 2. And we desperately wanted I plus 1 to be bigger than equal to 2 because that's what allowed us to use this formula right here. Here's the thing though. Our I definitely has to be bigger than equal to 1 to make I plus 1 bigger than 2. That needs to happen. But the problem is that we don't have enough base cases. What? Yeah, look at this, right? Look at this. In order for this strong inductive proof to make sense, right? We need to look at kind of like the first one that comes up. So if we're trying to prove this for all I bigger than equal to 1, that means F2, right? For all I bigger than equal to 1, we're trying to prove Fi plus 1. So that means Fi, so 1 plus 1 is 2. So that means F2 was the first one that we're proving with our inductive step. Should have the F2 is less than 2 squared. And so if we go through our argument, right, we're saying, oh, okay, this is all true because yes. Here was the issue. The issue was right here. Just to assume that Fk is less than 2 to the k for all integer k such that 0 is less than equal to k less than equal to I. But this is not true. F0 is 1, which is not it's not less than or equal to 2 to the 0. Oh, sorry. It's not strictly less than 2 to the 0. That's not true. F0 is not strictly less than 2 to the 0. So, right, we cannot assume that Fk is less than 2k for all integers between 0 and I because, well, it's just not true for 0. We need a 1 here. That needs to be a 1. Okay. And so actually we want only a 1 here, and we want a 1 here. But here's the thing, right? We know that starting at 1, it works out. So you can just brute force show at 1. 1 is in fact less than 2 to the 1, which is 2. So we know that at 1, it works out. But what breaks down here? What breaks down is if we assume that I is greater than or equal to 1, we only get that I minus 1 is greater than or equal to 0. And before we said, oh, 0 is equal to I minus 1, which is less than or equal to I. But that doesn't mean crap anymore, right? We need I minus 1 to be bigger or equal to 1. Because if I minus 1 was 0, well, then we couldn't say that Fi minus 1 is less than 2I minus 1 because F0 is not less than 2, 0. So we have to be very careful, right, that, that we only assume that our claim holds in this range where it actually works. And the claim was it worked for all I bigger than or equal to 1, right? So 1's going to be our bottom here. So the point is, we're actually going to need I to be bigger than or equal to 2. Because if I is bigger than or equal to 2, then I integer bigger than or equal to 2. What's that going to do for us? So if I is bigger than or equal to 2, then we're going to have that we assume 1 less than k is equal to I. Then note, since I is bigger than or equal to 2, by adding 1 to both sides, I plus 1 is bigger than or equal to 3, which is still bigger than or equal to 2. So, you know, we still get that I plus 1 fits this range of being bigger than or equal to 2, so we can use the recursive relation. By recursive formula, we still get this. Note, since I is greater than or equal to 2, which is greater than or equal to 1, 1 is equal to I, it's equal to I. So that all still works out. I is still going to be in the range that we're assuming the claim holds for. And so hence by our assumption, Fi is less than or equal to 2. So further, since I is bigger than or equal to 2, by subtracting 1 from both sides, we see that I minus 1 is bigger than or equal to 1. Thus, hence 1, let's equal to I minus 1, let's equal to I. So Fi minus 1 is less than 2 to the I. That was the key. That was the key right there. We needed to assume that I is bigger than or equal to 2 because we need to go 2 back. Or we need to assume I is bigger than or equal to 2 because we needed I minus 1 to be bigger than or equal to 1 because we want the claim to hold for I minus 1 because we want to use I minus 1 in the formula here. We'll talk about strategies to figure out exactly what this is next week on Monday. But the point is, we need that to hold, and once all that holds, everything works out. So for our base cases, though, what do we need to show? We're trying to show that it's true for all I greater than or equal to 1. And so we want to show P of 1. We also want to show P of 2, right? Because whatever our last base case is has to line up with I greater than or equal to 2, because that's when the recursion takes over. So it needs to pass the torch. So to prove P of 1, all I have to show is note. So all I have to say is that note F1 equals 1, which is less than 2 to the 1, right? Because that equals 2. Also, we can note that F2, right, by a recursive relation equals F0 plus F1, which by definition equals 1 plus 1, which equals 2, and 2 is less than 2 squared, which equals 4. So that means it holds for 1 and 2, and then we've shown that it holding from 1 all the way up to I for any I greater than or equal to 2 means it'll hold for the next one, and that's where the chain reaction takes off. So we have a little bit of technicality here, making sure that our I was high enough to make sure that we never went below I equals 1 in any of our assumptions here. But anyway, that's what we got there. That is our extra example. So I hope that this was helpful. Email me if you have any questions about it, because I have no one here to ask me questions, except for myself, which is why. Why do I do what I do? And that is for the love of math or you guys. Don't even choose. Anyway, have a great day, everybody. I'll see you guys later.